Good afternoon, everyone.
Good afternoon.
Today we will talk about time domain analysis. I already uploaded the PPT in the group, right? The group, in QQ group. I already uploaded the PPT. Read it before you come to the class. This one, you have it in your group, QQ group, in the class group. I try to upload all the PPT before the class so that you will study that before come to the class. If you don't know any terminologies like words, you can translate it so that you can understand it. That's our new chapter, time domain analysis. We have covered different chapters like transfer function, block diagram, mathematical modeling, signal flow graph. Now we will learn how to analyze the control system. There are two types of analysis. In two different domains, we can analyze our control system. One in time domain, another one in frequency domain. Time domain and frequency domain. We will learn both analysis here in this course. So first we will learn the time domain analysis. Time domain analysis are having two type of systems. First order system, what we are going to discuss today, which is this. Suppose 3 by s minus 2. Here, this one, s minus 2 equal to 3, which will give you s equal to 2. That is pole. One pole. If your system having one pole, that is called first order system. You have seen that in transfer function. In the transfer function. And like, suppose if I give another example, like 5 by s plus 5, s minus 6. So the pole will be s plus 5, which will give you s equal to minus 5. Minus 6, which will give you s equal to 6. So the poles here, minus 5, 6, two poles. That is second order system. And we have one pole here, that is first order system. We will study the first order system first. This first order system will be covered by 2 lectures today and the next lecture. Then we will talk about second order system in the next week. So time domain analysis will be covered by 3 lectures. So what is the time domain analysis? What is the definition? What do we understand by this word? Time domain analysis. It is analysis in our dynamic system. In time domain, if the input is given in terms of time, if the input is given in terms of time as a function of time, suppose here this xt, it is a function. This is an input, but this input is in a function of time. This input will send it through a system. This we call system, control system. Then there will be an output yt. So this one we call it impulse response ht, which will give you yt by xt. Impulse response. Now, this is what we need to find out, yt by xt. If an input is given in terms of time and it's sent through a system, the system can be anything. This Suppose dt inside there is one thing, one system, differentiation, integration, anything here. It goes through the system, and the system will have different types of operation, and there will be an output y, then the ratio of output by input. That is what we call the transfer function we need to find out. In time domain, we are going to impulse response. So time domain analysis is a response of a dynamic system if the input is in terms of time, given in terms of time. Now, if we know the input, what is input? Xt. If we know xt, if we know the system means mathematical modeling, then we can easily find out yd because we already know how to do the mathematical modeling. We had the chapter before we discussed how we can do the mathematical modeling, write the different types of mathematical equation from a system. But if we don't know the inputs, then what will happen? If we don't know, but because it is a dynamic system, the input is not known fully all the time. The input is cannot be known because dynamic system means it is a practical system, it is always changeable system. If the system is changing, the input is changing. Suppose now here the weather, what is the weather? It is up higher. It is not very cold, but in the evening the weather will be very cold. In the morning it was very cold. The input, the weather, it is always changing because it is a dynamic system. The practical system, real world system is a dynamic system. So suppose there is an example in the GPS. If we talk about the GPS, it is not fixed in one place. GPS is traveling everywhere. GPS. So when the GPS is running everywhere, the position, the speed of the GPS is not all the time known. It is varied. It is a random signal, random inputs. So because of that, it is very difficult to find out the actual input signal mathematically by simple equations. This is the problem in our dynamic system, that which type of input it is, because the input is always changing. So what are the changes? There are certain changes, like the input in time domain system. There can be 4 types of changes. 1, sudden shock. Suddenly it will change, shock. Sudden change, low to high. Constant velocity. Velocity is constant. What is constant? Velocity, v. Speed, constant speed, v. Constant acceleration, a. It is constant. Constant means fixed. So the characteristics, the input characteristics, changes characteristics divided 4 types. 1, sudden shock. Shock means this. This is shock. Suddenly change. This is what is sudden shock. Sudden change. Low to high. Low to high. This is change. Step. Change. Low to high. High to low. Or constant velocity, constant acceleration. 4 types of changes. According to these 4 types of changes, there are 4 standard signals. There are 4 standard signals. One we call impulse signal. Impulse signal because of the sudden shock. Sudden change, step signal. Constant velocity, because of that there is a constant velocity signal, that is called ramp signal, ramp. And constant acceleration, because of this there is another signal, constant acceleration, that is called parabolic signal. 4 types of signal, because 4 types of changes in the input. So we will talk about each of the standard signal one by one. 4 signals. So first of all, we will learn impulse, then step, then ramp and parabolic. Another important signal, that is called sinusoidal signal. What is this? It is also very important, sinusoidal signal, because we always have. It is a deterministic signal, sinusoidal signal, deterministic signal. We also can have this type of input. So it is a sinusoidal signal. But mostly we will focus on these 4. Because this is deterministic, it is much more easier to find. Impulse signal, I already told you, if there is a sudden shock. Sudden shock, in electrical engineering, we call it transient. Transient, suddenly there is a fluctuations. Suddenly there is a fluctuation. Like this light is lit now. Suddenly turn off and on. Suddenly turn off and on. That is called transient. So when it happens, that is called the sudden shock, and which can be defined by this, like this. And this value is A. We are considering the value amplitude A. And below, less than 0 and greater than 0, all the values is 0. So because of the sudden shock, suddenly in at once, one time, there is an amplitude. Because of that, which is that we define it t equal to 0. T equal to 0, the value is A. And t is less than 0, greater than 0, all value are 0. That means while t is not equal to 0, all the values are 0. Impulse signal, we define it by delta t, delta. Remember this, when you see this is the delta signal. It is a sudden shock and impulse signal. Now, if this value A is equal to 1, that is called unit step, unit impulse signal. 1, we define it for unity. So, if A value is equal to 1, that we call unit impulse signal. So, the impulse having one impulse, one pulse here, only one pulse, and rest of the pulses are 0. That's why we call it impulse signal. Here, look at this. We have an impulse. It is pure DC, and in the pure DC, suddenly there is a pulse. Suddenly there is a pulse. Very short amount of time. Here, there is also a DC. Suddenly there is a pulse. Here, there is also a pulse. All are the impulse signal. Second one, step signal. Step signal mostly defined if there is a sudden change. Sudden change, step change. Step means high to low. Here, high, then I am going low, step, that is called step, going high to low, low to high. So, that is called a step. So, step changes, how it happens? So it happened only, it is defined by UT, step signal is defined by UT. Step signal happens if there is a train of impulses. Train, not only one impulse, train of impulse. What does it mean? Train of impulse, look. 1, 2, 3, It goes on, train of impulse, train of impulses. It goes to infinity. If there is a train of impulses, not only one train, then we can draw it in this way. Because all are having same amplitude. So we can define it in this way. That's why here, look at this. You see it like this. It goes on till infinity. So if t's value is greater or equal to 0, start from here and it goes to infinity. Not only one impulse, series of impulses. Then the value will be a. Here, look at this, the amplitude is a. But if it is less than 0, the value is 0. So ut is equal to 0, and t is less than 0. That is called unit step signal. If this a value is equal to 1, then we call it unit step signal. A value 1, amplitude is 1. We will call it unit step signal. So you see here there is a step change. This is low, high. So the step changes to low to high. So that's why we call it step signal. Sudden change. Third one, ramp signal. Ramp signal if there is a constant velocity. Constant velocity, like here, look at this. This is a straight line. If we draw a straight line, that is called y equal to x, or y equal to mx. Mx is if m is equal to 1, then we call it y equal to x. So what is this? It is a straight line where there is a constant a, the slope. There is a slope a, constant slope. It is having constant. The a changes is a, linear changes. Ramp signal with slope a. So whenever there is, while it goes to infinity, till infinity, there will be a slope of a. Here there is a slope of m. Here there is a slope of 1. So if there is this value a is equal to 1, that here 1. So the slope is 1. So we call it unit ramp signal. This a, it is the velocity, constant term. So we can write it a into t. A into t, because here y equal to mx. So what is that? Y is equal to at. Here x is t. For what is the condition? T is greater or equal to 0. From here, equal to 0 to greater. T is greater or equal to 0. And in this side, all the values is 0. So constant velocity if there is a constant slope. In the ramp signal, that is called the ramp signal. Ramp signal is defined by RT, R. Because of this ramp, it is written by R, so the signal is RT. To differentiate between signal, step signal UT, ramp signal RT. So that is another one. The last one, constant acceleration. We call it parabolic signal. Parabolic signal is defined by P. Parabolic. Parabolic. What is the parabolic? Parabolic look like this. Like this. It is called parabola. look like a parabola. That's why it is called a parabolic signal. When it happens, if you have a divided term. So this one will have a t squared by 2. 8 squared by 2. If there is a divided term in the denominator, then you will have a parabolic signal or exponential term. This is a parabolic signal. So this is happens only if there is a constant acceleration. What is acceleration? Acceleration A. What is this acceleration? Acceleration is dv by dt. Rate of change of velocity. Rate of change of velocity. Because there is a rate of change of velocity. So that's why we get this term 2. It is a differentiation. Because of that we get this term. Because there is a t squared. So we will get a 2. Now, the slope of A here, we have a slope. This is the slope of A. But if A equal to 1, then this one we call unit parabolic signal. Here A equal to 1. That is called unit parabolic signal. And what's the condition? T is greater or equal to 0, we have a value of 8 squared by 2. And all the value here, T is less than 0. All the values are 0 here. So it will start from 0 to infinity. 4 different signals as we have seen. Impulse, step, ramp, parabolic. We will apply, we need all these signals. That's why we need to discuss the signal before we study the time domain analysis. We will use all this signal as an input of this. Suppose in xt. Now, it can be any. It can be delta t. xt can be ut. xt can be rt. xt can be pt. Anything. Because input changes in a random fashion, and this random fashion is categorized by 4 different characteristics: sharp, change, step change, constant velocity, constant acceleration. And based on these 4 characteristics, there are 4 different signals are defined. So we need to use all the 4 signals for the 4 different characteristics. Now, mathematically, how can we get one signal to other? Impulse signal. If we have an impulse signal, delta t, we can do the integration. And we will get a step signal. If we have a step signal, we will do the integration. We will get a ramp signal. If we have a ramp signal, we will do the integration. We will get a parabolic signal. Like this. Integration of delta t dt is equal to what? Ut. Integration of ut dt, you will get what? Rt. And integration of Rt dt, you will get what? P. Parabolic. Do the integration mathematically, you will get another signal. That is the integration term. You can do integration to convert one signal to another signal mathematically. And if you want to get back from this to this, how can you do that? You will do the differentiation. If you want to get back this to this, if you have a parabolic signal, and if you want to get RT, so you will write it d by dt pt is equal to RT. d by dt RT is equal to ut, and d by dt ut will give you delta t. So you can convert one signal to other signal. If you have one signal, you can convert to other signal by using integration and differentiation. Okay, now let's talk about the Laplace transform for all these four different signals. Laplace transform. First one, Laplace transform of impulse signal. Laplace transform of impulse signal will give you just the value, because this is just an amplitude delta t is equal to A. And while you convert this, you will get only 1, because delta t equal to 1. Delta t is equal to 1. Laplace transform. So while you convert Laplace of delta t, so you will get what? You will get just A. Because delta t, Laplace transform of delta t is equal to 1, so you will get just A. But if you convert this step signal, again the same thing. But now here there is a train of impulses, and still the amplitude is A, but Laplace transform of ut will give you 1 by s. Now you have A, so it will be multiplied. So Laplace transform of ut will give you 1 by s. 1 by s into A. We have A, so it will be A by s. Laplace transform of u delta t is giving a value of 1. So we are multiplying with 1 into A. That's why it is A. But Laplace transform of ut, unit step, is giving a value of 1 by s, which will be multiplied with A. That gives you value A by s. Next one, Laplace transform of ramp signal RT. So Laplace transform of t will give you a value of 1 by s squared. We have an AT. T will give you 1 by s squared, so it is A by s squared. And the last one, Laplace transform of t squared will give you 2 by s cubed. So here we have t squared by 2. T squared by 2, which will give you the value of 2a by s cubed, because there is a 2. There is 2 by s cubed. So 2 by s cubed into a. These are the Laplace transform for 4 different signals, because we will need this while we do the analysis. We cannot do the analysis in time domain. Whenever we do the mathematical analysis, we must need to convert time domain into frequency domain. So because of that, frequency domain, we need to use the Laplace transform. So if we convert each of the signal in frequency domain, we must need to know how to convert each of the signal in Laplace by using Laplace transform. So 4 different transform for impulse, step, ramp, and parabolic. It's very important to understand and remember this all. Now the time response for a dynamic system. Time response means if the function is given, if the input is given as a function of time, what is the response time in the output side of our dynamic system? So suppose this xt. What is the response? How do you find it? By using impulse response, by finding the ratio of yt by xt. If it is asked to the output is the output, whatever the output will be given. But if it is asked to find out the response, that is the time response, that is the impulse response, that is ht, which will be given, you can find out the ratio by yt by xt. So time response of a dynamic system is the response of an input if it is expressed in terms of time. Like here, two signals are given, two input is given, one input. This is UT, unit step or step. This is delta D. So for each of these input will send through the system, any type of system, random system we are considering, and the system will give you an output YT, and this is the input. Look, this is your input, and which will give you an output. Now you need to find out the ratio output by input. Impulse response. To find out the ratio, impulse response, to see what is the time response for this system. Again, here we have a delta D and there is an output. So you need to find out the HT, the impulse response, to find out the time response of the system. So the time response of our control system, any control system are having two components. Time response are having two components. One transient component, another one transient response, another one is steady state response. Transient and steady state response. It is a very important property of a control system. Remember, try to learn it properly, because any control system will have these two responses: transient response and steady state response. So now we will talk about the transient and steady state response. So when the signal will provide a response, it will change. It will start from zero. It will start from the rest, and while it will start from the rest, it will reach to a stable point. It will take some time. It will not go directly. Look here. We have an input, step input, and this is the response. Response means output. Response means output. Now here there is an input. This is the step input. Step input fixed. Step UT. So for this step response, there will be a response in the output which will start from zero. Here, zero or rest, and it will reach to this point, and this point we call it or equilibrium or stable point. Look, the output will start from zero to, it will take some time. Look at this. This is the time. This is the time. It will not go directly. So you see here in this point, here we have two response. So these two response we call transient response and steady state response. Transient response, which will start from zero to reach equilibrium, the time required of our output to reach the equilibrium point, that is called transient response. And steady state response, the system reached to this point, steady state point. After that, whatever the response is, it is the steady state response. So, what is the steady state response? Steady state response means stable response. That means our control system is stable now. Any control system you design has to be stable. Like here, we already know how to define it. if there is all the poles in left half plane, then we call it stable system. Mathematically, graphically, we define that stable system. If all the poles in left half plane, that is called stable system. Stable system means steady state system, and that steady state system will provide you, will give the steady state response. So there are two responses: transient response and steady state response. So you see here, it is always changing. It is started increasing, and it reached to the equilibrium point. So it is not fixed. It's change. And steady state response is stable. Now the transient response depends on the system poles. How many poles? One pole in first order, one pole. Second order, two poles. Third order, three poles. System poles, not the type of input. So we can analyze the transient response by any type of input. Like very easy, step input. Step input. This is a step input. So we can analyze the transient response by using any random input, step input. But we will see different types of input later on. But if we just use only one input, random input, step input, it is very much more easier because the transient response depends on which type of system it is. First order, second order, third order. Because for the first order, the transient response will be one type. Second order, the transient response will be another type. And the steady state response mostly depends on the system dynamics and which type of input it is. Here in the steady state response, it depends on which type of input. Whether it is impulse, step, ramp, or parabolic. It depends on different type of input. Then the steady state response will change. So it is done examined using different test signals. Then we can find out, we can test the steady state response by using a theory that is called final value theory. It is in Z transformation. There are two theories: initial value and final value theory. So you can apply the final value theory and we can find out the steady state response. But here we will focus on transient response, not the steady state response. So we will learn different types of for transient response for different types of inputs. Like here, the first order system, I already told you, the first order system are having one pole. One pole here, 3 by s minus 3. There is a pole, one pole in 2. That is the first order system. So we can define it like this: k by ts plus 1, where k is the gain, DC gain because we are defining it is a DC, pure DC. Step input, it is a pure DC. So we can define it as DC gain, and t is the time constant. So this k and t is unknown. We need to find out this k and t. The time constant is a measurement how quickly your system will respond, how quickly your system will reach to the steady state point. And this again is the ratio between input and output. We already know about the output and our input ratio, gain. What is the gain? Gain is the output by input. We know that. But which output? Which output? Steady state output. Steady state output. What is that steady state output? Look at this. This is the steady state output. Here, that is the steady state output. This is the output. This is also an output, but it is not a steady state. Here, this is the steady state output. So when the output reaches to this point, we will measure the gain. Output by input. Not here, not here, not here. Only in this point. Only at the steady state point. So K is the gain and T is the time constant. And now we will analyze this now. how to find out k and t. Suppose here, if we define this first order system 10 by 3s plus 1 a by s like k by ts plus 1. So k is 10, t is 3, right? Very easy. Now if we have another system like 3 by s plus 5, so how can we define it? We have an equation like this, k by ts plus 1, but this is not look like this. So how can you find it? So we need to find out like this ts in here. So, and here we need to make 1, but it is 5. So we can write it 1 by 3, 1 by 5, s plus 5. Because we are dividing, multiplying with 1 by 5 here, we will do that same in the denominator. So here we have 3 by 5, and here 1 by 5 into s plus 1. Now here it is look like k is t, 3 by 5, t is 1 by 5. So 3 by 5 and 1 by 5, k and t value. We can find it like that. So this again is 3 by 5 and time constant is 1 by 5. Now consider the following first order system. Now we are considering that here we have an input. This input is impulse input. Impulse. So how the system will behave? What is the transient response? So if we have an impulse response as an input in this system, so first of all you can convert this in Laplace domain. It will give you 1 because we have unit impulse signal 1. So it will give you the value of 1. Now Cs equal to k by ts plus 1. Now here k by ts plus 1, this system is given, this is the first order system, k by ts plus 1. Here we have Cs. So if I want to find out, consider the following of the first order system, and now if I want to find out the transfer function, how? Cs by Rs. Cs by Rs. We need to find out the Cs by Rs. So this Cs by Rs is equal to, we can write it, this is the transfer function k by ts plus 1. Now, what is the value of Rs? Rs is the delta S here, which having a value of 1. So this is just 1. So we can write it Cs is equal to k by Ts plus 1. That's why it is written Cs equal to k by Ts plus 1. Now what we need? We need to analyze this. So to the analysis, what we need? We need to apply Laplace transform and inverse Laplace transform. I want to find out the impulse response. So that we need to find out, here it is given in Laplace domain. We need to convert it in time domain. So how can you do that? Let's take a break, then I will continue this.